Now it's time to introduce some more logic gates. And these logic gates are really useful. Let's talk about the first one that I want to mention, which is the exclusive OR gate. The exclusive OR gate, again, if we start with our truth table of two inputs, x, y, and output f. They're all of our choices. Exclusive OR means that only one of the inputs can be a 1 in the two input case. So whereas the OR, exclusive OR, is often written as XOR, or some people say XOR. So whereas in the OR, this 1-1 case was also a 1, in the exclusive OR it's a 0. Now if you extend exclusive OR to more than two inputs, you get a 1 output when you have an odd number of 1s. Now, why is the exclusive OR gate so useful? Oh, by the way, this is what it looks like. It looks like an OR gate, but it has an extra little bar here. So this is the XOR gate. So this is extremely useful in addition. You'll be seeing the use of exclusive OR gates a lot, and also in error checking, which we'll get into later on in this course. Alright, so another thing to mention about the exclusive OR gate is it's sort of hard to find the exclusive OR function in K-maps. I just wanted to point you to this section in the textbook that talks about Karnaugh maps and exclusive OR, exclusive NOR functions. I'll tell you about the exclusive NOR in a moment. These can be only seen in the K-maps as diagonal groupings, or sort of these banded, large striped banded stripes in the K-map. So here, as you can see, this is sort of a diagonal of a grouping of 2. So you got some diagonals going on in the K-map. Here you've got some nice banding going on. This is indicative that you might be able to reduce down to an exclusive OR or exclusive NOR function. And here again, in the 4-variable case, we've got a nice band going on right here, which reduces down to an exclusive OR. Yes, so that reminds me, the symbol, remember OR was a plus sign. Exclusive OR is a plus sign with a circle around it. Alright, the next gate that we want to look at is the NAND gate. And this just pretty much means not and. So it's the same thing as an AND gate followed by an inverter, because you get the output of the and then you NOT it, or you take the inversion, and that's what you get. So the symbol is just a reduced form of this, which is just the and with a dot at the front. So what does this look like in the truth table? So we have x, y, and our output. Let's first look at a, x, and y, and then we can look at x NAND y. So remember, our and, we only got a 1 if all of the inputs were 1. And now with NAND, we just take whatever and was and invert it. So these are all 1s, and this is a 0. So that is the NAND function. The NAND function, this would be A NAND B. Or you could write it like this, A NAND B. It's just and inverted. Alright, and we've got one more, which is the NOR function. And guess what? This is not OR. It looks like the OR gate with a circle in the front. And again, we have x, y, and OR. Let's say x OR y, x NOR y, And remember, with the OR, we got all ones. If we had at least one 1, and so the NOR, we only get a 1 if we don't have the ones. So X NOR Y gives us this, and you could write it as X NOR Y, or X NOR Y like that. There you go. So then again, the X NOR would be taking this XOR and inverting it, 1001. So this is our XNOR, which is going to look like the XOR gate with circle. Okay, so I told you why the XOR and XNOR gates are useful, but why is NAND and NOR useful? Well, these two gates are known as functionally complete, meaning that all you need to have in your toolbox is a whole bunch of NAND gates or a whole bunch of NOR gates, and you can create every other gate that you want, an inverter, an AND, an OR, a NOR, an XOR, with just having a box of just an AND, or just having a box of just NORs. So these are really useful because you don't need to worry about buying a specific type of gate. You can just get a whole bunch of these and configure them to be any type of gate that you want. So for example, let's look at how do we make a NAND into an inverter. Now remember, the truth table for the NAND was going to be, we only have a 0 when they're both 1s, and otherwise they're all 1s. So let's look at this truth table. If you make the inputs the same, meaning X is the same as Y, you're going to get an inverter, because here X and Y are both 0 and you get out a 1. Here X and Y are both 1 and you get out a 0. So you can make an inverter by just tying the inputs together. So if you're interested in knowing how to use a NAND in all other configurations, good old internet will tell you that. And this is a really good site. If you look up here, cpuville.com/logicgates, this shows you how to make all of the NAND. Here is using a NAND to make an OR, and you can go through the logic to figure that out.